Okay, today we're going to be learning about NAND gates. And if you look at NAND gates, they're not and gates. Not and gates. Combined into one gate. And in order to really look at this, let's look at some truth tables. An and truth table, if we're looking at and, X and Y have to both be 1 for the Z output to be 1, right? So X and Y is 1, so the output is 1. The rest are zeros. Okay? And if we look at the NAND gate, this is a not and gate. Not and gate. So we're looking for when it's not an and gate. Okay? So the only place that it's an and gate is right here when the outputs are both 1. That is when it is an AND gate, so it is not 0 an AND gate. The rest of the places are 1s because it's not an AND gate here, it's not an AND gate here, it's not an AND gate here, but it is an AND gate here. So we're looking for when it is not an AND gate. That is when the output is 1. Okay? If you need to understand this more, go back, just rewind, watch this again, so you'll understand that an AND gate, X and Y are 1. The output is 1. When both X and Y are 1, the output is 1. When both X and Y are 1 in a NAND gate, that's a not AND gate, all right? We're looking at a 0 at that output because it is an AND gate, and a NAND gate is a not AND gate. Okay, so let's actually look at these gates. If we look at the diagrams of these gates, an AND gate looks like this. Okay, we have X, Y, and Z, all right? And a NAND gate, we have X, we have Y, all right? And if we remember back to a question on one of the activities that we did, it asked about the little circle in the inverter gate. Like what is that? That means it's inverted, okay, or the not circle, okay? So the not AND gate, we have an AND gate, and then we're gonna say that it is not an AND gate. We have our output Z, okay? This is what a NAND gate looks like, or a not AND gate looks like. Okay, in this lesson, we're gonna be making circuits completely from NAND gates. And what a NAND gate is, all right, is a universal, and what a NAND gate is a universal gate. And what that means is that you can create, okay, so we need to understand that the NAND gate is a universal gate. So we can create all other gates from a NAND gate. You might think, well, that's impossible. Well, I'm gonna prove it to you. Okay, so if we look at an inverter gate, we know that it looks like this, okay? We know that it looks like one input coming in with a triangle, X, all right, and an output Z, all right? If we look at it as a NAND gate, if we look at it in the NAND form, okay, we can see that we have one input and we have a NAND gate, all right, with one output, all right? But an AND gate has 2 inputs, so we have to have 2 inputs coming in. We're just going to split this, and we're going to say that's going to go in there, and that's going to go in there. So X is going to split up and go into the NAND gate, all right, and come out as Z. Okay, we have the output Z, but what is Z? Let's figure it out real quick. So we have on the outside, we have X and X going into the inverter. We have, because we have X and X right here, we have X and X, all right? And then going into the inverter, we have X and X naught, which equals X naught. We have X naught and X naught really coming out of here, so we have X naught, okay? So that's what that equals, okay? That's how the NAND gate acts as a inverter gate. All right, so let's take a look at how it acts as a AND gate. An AND gate, we know, looks like 2 inputs, X and Y, comes out Z, and we get Z equals X and Y. All right. Now, if we look at it in the NAND form, okay, we're going to use the NAND gates to form an AND gate. All right, so we have input X and Y, and we have them going into a NAND gate. All right, so not AND. So what do we have right here? We have X and XY in this section, and then right here it inverts it. So right here we have not X, not Y. All right, and then we have to invert that back. So we can have X, Y. All right. So we need to do the same thing. We need to invert this. So what we're going to do is we're going to take this section up here and we're going to put it in down here. So we're going to split the signal. And then we have X naught, Y naught in there, and then it inverts it back to XY. We have XY. They're perfectly equivalent. And now let's look at it as a OR gate. Okay, in order to make this an OR gate, we need to remember that an OR gate has two inputs with the curve. It looks kind of like a rocket ship. We have the output Z, input X, input Y, and Z is going to equal X or Y. All right? So we need to, first of all, understand that this is going to take 3 NOR gates, okay? Or I'm sorry, not NOR gates, NAND gates, all right, to create an OR gate. So let's see here. We need an X and we need a Y. We have an input X, we have an input Y. So in order to make an OR gate out of NAND gates, all right, this is NAND form, we need to, first of all, attach a inverter NAND to X and Y. So we're going to make an X naught and Y naught. So we need to split the signal on X, take it into a NAND gate, and come out we have X naught. We need to split the signal on Y, take it into a NAND gate, and we have Y naught. Okay? And now we're going to bring those two signals together inside of another NAND gate. All right? So we have X naught and Y naught, and then we come into another NAND gate. All right? And we have X naught and Y naught coming into here, and then it inverts it here. So out of here, we get X naught, Y naught inverted. Okay, now according to De Morgan's theorem, we can split the line and change the sign. So De Morgan's theorem says we split the line and we change the sign, and we get X double naught or Y double naught, X or Y. And that is how we make these gates from NAND gates. The NAND gate, again, is a universal gate. That means we can create all other gates, the AND gate, the OR gate, and the inverter gate, all from a NAND gate. And again, a NAND gate is a not AND gate. Okay, just for the sake of a quick example, let's look at this circuit right here. We have the SOP expression X naught Y, X naught and Y, or Z naught. And we want to create this using only NAND gates. So let's see, we need to invert X, so we have the input X, input Y, input Z. All right, we need to input X, so we're going to split the signal, and we're going to put it into a NAND gate, and we get X naught coming out of there, okay? And then we need to put that into Y, and so we have Y, X naught right here, and we have Y here. So out of it, we need X naught and Y. So we need to put it into a NAND gate. If we remember the AND gate, all right, we have X naught Y right here. So coming out of here, we're going to have X naught Y, all right, like that, all right. And then we need to split the signal again, and we come out with, so in right here, it inverts to X naught Y naught. Okay, so right there we have x naught, 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 and we know that that all simplifies down to be x naught y, all right, x naught y, and then we need to add it to an OR z inverted, okay, OR z inverted. So we need to invert z. It needs to all go, all right, and remember that this takes an OR gate takes 3 NAND gates for it to become an OR. So we need to invert, I'm going to draw this down here a little bit. We need to invert this signal. And this is all patterns, okay? And these will be available to you so you can remember. And we need to invert this signal. So we have z naught naught right here, and we have x naught y naught right here. All right, so then we need to AND these together, or NAND these together, and we get x naught naught y z naught naught knotted. Okay, so we split the line and we change the sign, and we get split the line. We have to use De Morgan's theorem. Split the line, change the sign, and we get x naught y double knotted or z triple knotted, and then that all simplifies down to be x naught y or z naught. And you can see that we can create all circuits with the NAND gate, which is a universal circuit or universal gate.